Hello Year 5 and welcome to your new science topic for this term. So our topic for this term is going to be forces in action. Okay, so we're going to be looking at a lot of all these different forces and looking at the physics side of our science lessons. So the first lesson we're going to start off with is what is gravity? So this links a little bit to what we learned in our space topic from last term. But we're going to dig a little bit deeper into it today. So what we need to be able to do by the end of this lesson is understand what weight is. Okay, so we know what weight is and compare it if we talk about it in the terms of somebody's body weight, how heavy they are, how light they are, how heavy something might weigh, but how that weight is changed when you talk about it in the concept of space. Okay, we're then going to look at defining what gravity is, because we haven't really covered much of what gravity itself actually is. We're going to look at that force today. Then we're going to look at understanding how gravity works. I'm going to show you a video of astronauts walking on the moon. And then we're going to have a go exploring the effects of gravity through experimenting with craters, okay? So for this lesson, your experiment you're going to do almost alongside the video. So it's not necessarily going to be an activity just at the end. If you don't want to, you can do it during the video as well. I'm going to show you my version of the experiment and then you guys can have a go. What you're going to need though, if you have it at home, don't worry if you don't, because you're still able to watch the video. But if you do have it at home, you'll need some flour. You may need a couple of bags of flour and some cocoa powder or some hot chocolate powder or something that you can then cover very lightly over the top, okay? So let's have a talk about what weight is. I'm going to pause the video and have a think. What is weight? How would we define it? Can you think of some examples? Is it different here on Earth? Is it different in space? Just pause the video and just brainstorm some ideas of what is weight. Okay, so weight is the word that we use to describe how heavy something is. Okay, so something weighs a lot or it weighs very little. Okay, we're talking about how heavy or how light it is. But when we're talking about it in terms of Earth, we've got the Earth's gravitational force, which causes objects to have weight. Okay, so we know if you bounce up and down on a trampoline, when you bounce up, that gravitational force makes you heavier than you actually are and pulls you back down to touch the trampoline. Okay, hence why we all stand on the Earth. We're not all floating around in the sky. Now, the idea of what gravity is a force. So it's not something you can see or feel or touch. Okay, but it's a force that's within our atmosphere, within our solar system, that pulls objects towards the centre of the Earth. So you imagine like the centre of Earth's got a magnet in it, and we all have the opposite attracting part of that magnet. Okay, we are all stuck to that part of the magnet. Okay, so whatever comes up must come back down again. So when you bounce up on a trampoline, you come back down. You bounce a basketball off the floor, it bounces up, but eventually it comes back down. Okay, so that gravity that's within our atmosphere on our planet is what keeps us all attached to the Earth. It's what keeps the buildings attached to the Earth, the trees. Everything is stuck and pulled towards the centre of the Earth. So you have a copy of this at home or at school in front of you. What I want you to do is think, what do we know about gravity at the moment? We know that gravity pulls everything to the centre of the Earth, okay? And we know that when we're on the planet, if we're up here and the other people down here in Australia, they're the other side of the Earth. And obviously we are spherical, we are a round spherical body. But that doesn't mean that the people underneath us are then stood on the planet with their heads. Okay, even though they're upside down to us, they're still stuck to the Earth. So what I want you to see if you can do, can you draw the arrows, these rain clouds, okay, I'm going to now rain, okay? I want you to see if you can draw in the direction of the rainfall and where it would fall on this diagram. So think about what happens with gravity and everything pulling to the centre of the Earth. Can you draw lines coming from these clouds to show where the rainfall would go? Okay, so it's going to go towards the Earth. Okay, so your diagram should look a little bit like this. Your raindrop should be going towards the centre of the Earth. Even though we're up here and other people are down here, that doesn't mean the rain's coming in upside down, because where you are on that Earth, you're stood upright, okay, because of the way that gravity has pulled you down to the centre of the Earth. So we usually think of gravity pulling everything down, okay? But it doesn't necessarily pull everything down, because if you think about it, I'm stood upright right now, and the gravity would be pulling down from above me. But if I was in Australia, I would technically be stood upside down to the way I'm stood now, which means the gravity would be pulling me in the different direction. So rather than saying that gravity pulls everything down, all it does is it pulls everything to the centre of the Earth. So imagine you have a ball, okay, and you've got lots of little pins in your ball. I could put a pin in the North Pole and a pin in the South Pole. I've not necessarily pulled it down or stuck it into that ball. Okay, but that gravity's allowed both of those pins, okay, to be in the north and south of my ball, okay, which effectively would be my Earth. If I covered all of that ball in all these little pins, they would all be drawn towards the centre of that ball rather than all being pulled down, because they'd all be facing the direction. So gravity, you have to remember, pulls everything to the centre. So imagine there's like a magnet in the middle of our planet, okay, and everything is pulled towards it no matter which direction, okay. So here you can see that's why it makes it look like the rain here is actually raining upwards, or the rain here is raining sideways. But actually it's not, because if you imagine where you're stood here, you'd be facing in this direction anyway, so the rain would be coming down on top of you. So it's important to remember, imagine it's like the magnet in the centre of the Earth. So here's an interesting question then, before I show you that video. When astronauts walk on the moon, they bounce instead of walking. And I wonder if you know why it is that they don't just casually walk like we do. And can you describe what you think it would be like to walk on the moon? So think about what you already know. If you've ever watched the moon landing, okay, and you know about gravity and you've seen the original video of one small leap for man, one giant leap for mankind. Think about it in that concept of what that giant leap might represent and why the atmosphere, the surface atmosphere on the moon might be different to our planet. So just pause the video, just have a think about those two questions. Okay, I'm actually going to show you part of this video, okay, and I'm going to show you what it was like for them to be on the moon.
And Tony, the rover tracks are just, they're barely sinking in.
See how he's bouncing there, he's not walking, he's bouncing.
Too far down in the middle of the... Again, drop. There it is. Okay, I've got it in there now. Hey, John, this is perfect with the limb and the rover and you and Stone Mountain and the old flag.
Yeah, it's moving very slowly. It's also bouncing with the moves, but it's very slow.
That's a pretty outstanding picture here, I tell you. Come on a little bit closer.
Okay.
Okay, here we go, a big one.
Go jump.
Off the ground, before. There we go. Good.
So could you see in there how closely they were able to bounce, okay? But you can see how slowly they did it as well. Now, although that we do the same thing on our planet, when we bounce up on a trampoline or jump, we come back down again. Now, the same thing happened to them on the moon. But why would they be moving slower on the moon than we would on Earth? Well, they have a different gravitational pull. Okay, it's how they have what's called in space zero gravity. There is no magnetic force or gravitational force that's pulling them towards the center. So had they then jumped off far enough, they've just floated around space. Okay, so it's a little bit different being up there than it is being down here. So one of the ways that we can see the effect of gravity, because obviously we don't all get to go to space and bounce around on the moon, okay, in zero gravity and experience what it's like to be weightless. But what we can see is we can see the effect that gravitational pull has when things like asteroids or meteorites come crashing down into the Earth. And when they do crash down, we know from meteorites, when they come through our Earth atmosphere, they speed up, don't they? Because they burn the gases as they come through the layers of our atmosphere. And obviously, once they come piercing through our atmosphere, what does gravity do? Well, it pulls it, okay? So that picks up speed as it comes crashing down to our Earth. Now, when it hits and there's that impact, okay, on our planet, it creates a massive hole, okay? Now, that hole is called a crater, okay? And it's almost like a hole that's in the middle and then it's got steep slopes that go up over to the side. And that is called a crater, and that's usually almost like the crash site of where a meteorite lands on the Earth. Now, how might the size and the shape of a meteorite affect the size and the shape of the crater, okay, that leaves the impact on the ground? How do you think that has a difference? Do you think if it's smaller, it would make a smaller crater? If it's bigger, it might make a bigger crater? Just have a pause and think about that question. Okay, well, the more a meteorite weighs, so you have to consider that it weighs less when it's in space. Obviously, when it comes through our atmosphere, obviously it picks up that weight because obviously it's being pulled. So the more it weighs, when that lands and that makes impact, that's going to make a much deeper crater. Now you imagine if you're baking a cake and you drop an egg into the flour, what happens to some of that flour? Yeah, okay. It comes out as dust, doesn't it? You get covered in flour, you get covered in icing sugar. So if you were to slam that egg down into the flour or slam the spoon down, you're going to create a bigger dust cloud, aren't you? Because you've put more weight and power into that punch into the flour. So the more it weighs, the bigger the crater is, the more dust that's going to go flying and the more earth and rock that's going to be loosened and then scattered, okay? Now it can affect, the size of the meter can affect the diameter. So the diameter goes from one side to the other. So you've got the radius, which is the middle point to the one edge of the crater, and the diameter goes from one side to the other. So the size of it can affect how big it goes from one side to the other, okay? Now, one of the clearest places to be able to see craters is on the moon, okay? If you've ever seen pictures of the moon, or if you've ever watched Wallace and Gromit, and they go on their adventure to space and they come back and they cut up different bits of cheese, you can see the craters and they're very, very defined shapes, okay? Now, the reason why they're very defined is because there is no gravity. Okay, so now that they've walked on the moon, when we had the moon landing, the footprints are still there on the moon. Okay, you make footprints in the sand over here and there's a storm, it's going to be washed away, isn't it? Or it's going to be blown away by the sand. Because there's no wind on the moon, that dust is laid perfectly settled. So when that crater lands, it doesn't move. It's there forever, okay? Because the dust can't blow off or be swept over, okay, and wiped clean, because there is no atmosphere. So it can't get blown away. It can't get eroded by the wind or the rain. We've looked at eroded. Eroded means where it starts to chip away at it. Okay, it stays there. Okay, and that is a great example of showing us what craters look like and the impact that they can have. So what I want you to do is, you're going to have a go at doing an experiment. I'm going to whiz through my example so I can let you guys go off and have a go at your own. So we're going to explore this. This is where you need your flour and your cocoa powder. So I filled up a tray here, okay, of flour at a depth of about 7 to 8 centimetres. So it's completely covered, okay. And I used a spatula or a ruler, something that you've got flat, just to measure it out, okay. Now on the top of it, I put a very fine sprinkle of cocoa powder, okay. So it's almost like another layer on the top. And what I did is I found some different objects that I had in my house. Okay, so I had a marble, I think I had a penny, and I had a ping pong ball. I think I also had a golf ball. I found stones off my driveway, and I had a rubber, okay, because I had my pencil case at home. And what I did is I dropped these different objects into the flour, and I need to make sure that I did them from the same height, okay, so that it made it a fair test as much as possible. And then what I did is I took some pictures, okay, and I measured the depth of how far that object went in, okay. So I used a little lollipop stick and then I drew a line and then measured it with my ruler, okay, just to see what the impact would have on the surface of effectively the surface of my moon is what I created there, okay. So when your tray is full of craters, what you want to do is stir the flour back around and shake it out so you level it off again. You can put a little bit more cocoa powder on the top, and then you can carry out the testing again on a clean surface. Now what I want you to do is, you've got the sheet at home to be able to fill out your observations from your experiment. And I want you to think about what you noticed, okay, and what conclusions you can draw from the experiment. So think about the objects you dropped in. How heavy were they? What did the height have in difference? What was the depth of it when it created that crater? What was the spread of the cocoa powder as it splashed across? And think about what it is that you can conclude from your experiment. Now, if you weren't able to have a go at doing this, if you don't have the flour and cocoa powder at home, that's fine. There are videos on the internet for you to be able to watch of someone conducting the experiment, or you can have a look at the photos I've done on here. But you can still have a go at filling out the sheets, okay, with all the different observations on it. See if you can find a video online. See if you can have a go yourself. It'd be a great experiment. If you do, please do take some pictures so I can have a nosy and see what you've done. But have a go at doing your crater experiment, okay, and then we will have a look at that in our next lesson for next week. Now I'm going to skip the plenary because I'm actually going to do that as our starter for our next lesson. So have a go at making your craters, write down your observations from your science experiment, and let me know how you got on. All right, good luck, year 5.